This video is designed to give you some idea as to how to do a sort of back of the envelope engineering estimation problem. So we'll have three problems here to look at, and each problem should start with an assumption. You should, or multiple assumptions, and these are things that you should start with something that you know as opposed to just taking a wild guess. So it would be a wild guess to just say, oh, I think it's 3 million paper clips for this problem. What we'd like to do is get something that's reasonable, maybe about the right size, kind of in the right power of 10. In order to do that, you have to start with something that you're comfortable knowing. So for example, we can start with the assumption that one jumbo paper clip, one PC is approximately 2 inches long. Now, this isn't perfect. We haven't measured one. Actually, if you do measure one, it kind of winds up being sort of 1.6 inches or something like that. But 2 inches is a good enough estimate. It's ballpark. We know it's not 2 feet, and we know it's not like 1/4 of an inch. So we're not way off, and that'll give us a kind of ballpark number. We also need an assumption about how far it is from San Francisco to New York City. So we're going to say it's about 3,000 miles. This is based on the fact that it's roughly, 3,000 miles across the country, give or take a little bit. Once again, this is not horribly far off. We know it's not 300 miles, because that'll barely get you to Nevada. And we also know it's not 30,000 miles, because that'll take you all the way around the world. So we're kind of in the ballpark, and that's the idea with these estimation problems. If you needed to, for example, buy a bunch of paper clips in order to actually do this, why, I have no idea, but there are plenty of problems that you do need an estimate for, and this is a good example of how you could do it, because you really don't have any idea how many paper clips it would take if you just guess. But if you work it out, you should be able to get a ballpark answer. So we want our answer to be in paper clips per distance, or distance to New York City. So those are the units we want at the end, which means we should start with paper clips over 2 inches. So one paper clip over 2 inches, and that gets us started, which means that if we can convert from inches to feet, and from feet to miles, and from miles to distance to New York City, we're going to have paper clips per distance to New York City. So we're going to multiply by 1, and that 1 is the conversion between inches and feet. And notice that we're going to put 12 inches over 1 foot so that we can cancel the inches, and now our units are paper clips per foot. And of course, if we did the calculation, we'd get 12 over 2, or 6. So it's roughly 6 paper clips per foot. That's also something you could have started with, because you could have had a good feel for that. Nevertheless, our goal is to start with something very basic, very much within the realm of your comfort zone, and then to work from there. So now that we're in paper clips per foot, our goal is to change from feet to miles. Excuse me. Somehow I put my... sorry about that. 5,280 feet per 1 mile. Now, of course, the feet cancel, and we are now in paper clips per mile. And if you multiplied all this out and divided by 2, you'd wind up getting an approximate number for paper clips per mile. But we don't need to do this until we're done, and then we'll sort out the answer. So we're now in paper clips per mile, and what we need is approximately 3,000 miles per San Francisco to New York City, and that'll get us our distance to New York City. This allows us to cancel the miles, and we're in paper clips per distance from San Francisco to New York City. Now it's a matter of simplifying this as a leading digit estimation problem. I'm going to write the whole thing down as to what we have numbers wise, and then do this as a leading digit approximation problem. So this means our answer is approximately 10 times 5 times 10 to the third times 3 times 10 to the third as well, over 2. That's going to get us, if we do an approximation, we can cancel. If we do some canceling, that's going to get us 5, and that's going to get us 5 times 5 times 3, which is 75 times 10 to the 6th when we put our tens together, which means that our answer is approximately 8 times 10 to the 7th, or 80 million paper clips. So there's a set of steps that can allow you to get a reasonable estimate. Now it might be, closer to, 100 million. It might be closer to 40 or 50 million, but at least we're in the ballpark, and we know that it's in the tens of millions roughly. So here's a stack of 10 million pennies, and we're going to try to put our answer in units that make sense. And what we're going to do is assume that, let's say, 10 pennies is approximately 1 inch high. This isn't a terrible estimate, but it's not necessarily bad. So we want our answer, let's say feet or miles. Let's go with miles per stack, since it's likely to be quite tall. Maybe we get half a mile or something, that gives us an idea, or if we get multiple miles. It's definitely going to be more than inches, and probably not useful in feet. So I would tend to start with 10 times 10 to the 6th, 10 times 10 to the 6th pennies per stack. And that means what we have to do is turn those 10 times 10 to the 6th pennies into a distance. And of course we can do that because we've connected the 10 pennies equaling 1 inch. So we could have started with that as our first fraction, but this way allows us to kind of realize that the stacks are going to stay the same, and we just need to get the pennies into some distance. So our next thing then would be to use that 1 inch over 10 pennies to get us to be able to cancel the pennies, and now we're in inches per stack, and all we got to do is turn that with a couple of conversion steps into miles per stack. So we're in inches, so that means 1 foot over 12 inches, and notice I put the inches on the bottom so that the inches cancel. That is equivalent to saying, oh, this needs to be 12 times smaller in order to get it into feet. There's 1/12 as many feet as there are inches. But just let the unit conversion procedure decide for you where everything goes. So obviously we put feet on the bottom again, so the feet cancel, and we've got miles per stack, which is the units we're looking for. So that means if we put the 10 times 10 to the 6th together, that's 10 to the 7th. So we have 10 to the 7th over 10 times, I'm going to roughly round 12 to 10 again, and again this is all leading digit estimation, so it's an approximate answer. Those are each 10 to the 1sts, and then 5 times 10 to the 3rd, and that means we're going to get approximately 10 to the 7th over 5 times 10 to the 5th. If we do some canceling, that's going to leave us with 100, 10 squared over 5, or approximately 20 miles. What that means is a stack of 10 million pennies is actually going to be 20 miles high, way taller than any building ever built. I think the tallest building ever built is pushing a mile, so 5,000 feet or so. So this is up there in the range. 20 miles is 100,000 feet. That's well above what an airplane would fly. This estimate might be a bit high because we rounded 12 down and we rounded 5,280 down. So that means the actual number is probably a little more like 16 miles or so, but clearly much too high for us to actually build or stack. Our final engineering estimation problem actually requires us to do an area conversion. So this is a little more challenging, and you have to remember you're converting from square units to another different square units. And so I'll show a sort of careful way of doing this. Our starting assumptions, let's assume one calculator is approximately 6 inches by 3 inches, and let's assume that the math room is, say, 20 feet by 25 feet. Those are rough numbers, nothing perfect there, but that'll do us. So we want our answer in calculators per math room. So here are the units we want. And with calculators per math room, so since our units are calculators per math room, we want to start with one calculator. And remember, this is an area problem, so we need to realize that 6 inches by 3 inches is 18 inches squared. Okay, so that's going to give us the requirement that we have to convert from square inches to square feet in order to get the math room. So one calculator per 18 square inches, and then in order to convert properly, what you're going to find is 12 inches per 1 foot times, times 12 inches per 1 foot again. And what that allows us to do is cancel inches squared with inches times inches, because inches times inches is inches squared. This now gets us into calculators per square foot, and we want to get it into per math room, which means that what we're going to need to do is multiply by 20 feet by 25 feet. So in other words, a product of 20 and 25. That's going to get us the area of a math room for one math room. And you'll see that our units of feet and feet cancel. Feet squared and feet squared are now canceled. So we are now in the units of calculators per math room, and we can simply sort out our numbers. Now notice what this means is we have 12 times 12 on the numerator, as well as 20 by 25. And on the denominator, we have roughly 18. So performing our leading digit estimation, we're going to take 12 and 12, and we know that 12 times 12 is 144, but we're just going to round 12 to approximately 10, and the other 12 to approximately 10, and we'll take 20 and call it 2 times 10 to the first. And since both the 12s got rounded down, it'll be nice that 25 gets rounded up and gives us 3 times 10 to the first, and that'll kind of compensate for the 10 and 10 approximations of 12 and 12. 18 we're going to approximate as 2 times 10 to the first, and now all we have to do is sort out our numbers. So I'm just going to cancel 10 to the first with another 10 to the first and a 2 with a 2, and we should be able to sort this out pretty easily as 3 times 10 to the third, or approximately 3,000 calculators to cover the math room. Okay, so notice that the key for doing these problems is that you're going to do 2 times each conversion factor if you're working with area. Similarly, if you were working with volume, you'd do 3 factors of 12 inches per 1 foot to convert from cubic inches to cubic feet, for example. Okay, I hope this all helps.